So I want you to imagine a massive disaster zone, like let's say it's a dense, just completely burning forest.
Oh, or maybe like a collapsed cityscape right after a major earthquake.
Yeah, exactly. Something where smoke and dust are just completely blocking your line of sight.
Mm-hmm.
And the twisted metal and concrete of the buildings are, scrambling all your radio frequencies.
Right, so you cannot fly a drone in there manually. It's not physically possible.
Right. But there are survivors trapped inside. So the question is, how do we send in a coordinated swarm of, say, 50 drones to search that entire chaotic area all at once without them just immediately crashing into the debris or, worse, crashing into each other?
I mean, it is an absolute logistical nightmare. You're dealing with a highly dynamic physical environment, zero visibility, and absolutely no central control tower to guide them through the wreckage.
Yeah, to pull off a rescue like that, you don't just need better cameras or stronger motors. You really need a hive mind. So today we are taking a deep dive into some newly published research from Tennessee Tech and Qatar University.
Yeah, this is a massive 2025 academic survey published in the journal Drones.
Right, and it basically proved that we are finally teaching drones to think as a collective. We're unpacking the incredibly complex and honestly fascinating world of multi-agent reinforcement learning.
To really visualize this, let's shift the backdrop here to a futuristic glowing schematic of a drone swarm flying over a topographical map.
Oh, I like that visual.
Yeah, because we are witnessing a fundamental paradigm shift here. We are moving away from drones functioning as basic remote-controlled toys and stepping into this era where they are autonomous, scalable, highly intelligent robotic swarms.
Swarms that are capable of decentralized decision-making in the blink of an eye, which is wild. And if you follow drone tech, you already know the old ways of doing things are just too rigid for a scenario like a collapsed building.
Absolutely. You just can't rely on pre-programmed GPS waypoints.
Right, because GPS is completely useless if a sudden obstacle falls in your path or if you fly indoors.
Yeah.
But why can't we just have 50 highly trained human pilots standing outside the disaster zone, and each one is just flying one drone?
Well, it really comes down to two major bottlenecks: human cognition and radio physics.
Okay.
So first, the cognitive limit. Think about a complex real-time strategy video game. A human operator might be able to command a few units by clicking around a screen.
Sure.
But dynamically piloting a single drone requires constant micro-adjustments to pitch, yaw, and throttle. So asking a human to monitor and adjust 50 drones simultaneously to prevent collisions in, like, a windstorm.
It's just cognitively impossible, like trying to play a video game with 50 different controllers at the same time.
Exactly. It's impossible.
So the human brain is the first bottleneck. What's the radio physics bottleneck, Glenn? Why can't we just build one massive, incredibly powerful transmitter that just blasts the flight commands to all 50 drones at once?
Well, because of what the paper calls impedance matching issues.
Impedance matching.
Yeah. In radio frequency communication, impedance matching involves aligning the electrical resistance of the transmitter and the antenna. And if there's a mismatch, which happens constantly when drones are banking, turning, flying behind thick concrete walls.
Oh, right, because they're moving so fast.
Exactly. The radio signal actually reflects back down the antenna line instead of radiating out into the air.
Wait, really? The signal bounces back into the remote control?
Yeah. Literally.
Yeah.
It causes a massive loss of broadcast power and can actually fry the transmitting equipment.
Oh, wow, that's crazy.
It degrades long-range communications significantly. So in a complex environment, trying to broadcast central commands to a massive swarm is just a guaranteed recipe for lost signals and 50 crashed pieces of hardware.
Okay, so if humans are too slow and radios are too fragile, we have to remove the human entirely. We need to give the drone a digital brain that can figure out how to fly itself based on what it's experiencing in the moment.
Right, and that brings us to the foundation of this entire technology reinforcement learning. In a traditional machine learning setup, you feed an AI massive data sets of images or text. But you can't feed a drone a data set of every single gust of wind it might ever encounter.
Right, nature is too unpredictable.
Exactly. So instead, in reinforcement learning, the AI learns by taking actions in its environment and receiving feedback in the form of mathematical rewards or penalties.
Okay, let's unpack this. Give me a visual for that. How does it actually learn to fly without a data set?
Think of a toddler learning to walk on the deck of a boat tossing in the ocean.
Oh, okay.
The toddler doesn't calculate the fluid dynamics of the waves or the exact angle of the ship. They just take a step.
Right.
If they lean too far left and fall, they get a penalty. It hurts. If they lean right when the deck tilts left, they stay upright. They get a reward.
I see.
Over millions of tiny micro-adjustments, they develop an intuitive policy for walking on a moving surface. The drone is doing the exact same thing with its rotors in the air.
But wait, if the drone is constantly processing its environment like that, doesn't it need massive amounts of memory? Like to remember every single mistake it made on that flight to know what to do next?
Surprisingly, no. And what's fascinating here is this brilliant mathematical shortcut called the Markov property.
The Markov property. Okay.
Yeah, it's a rule built into the framework of these algorithms, which basically states that the probability of the drone's next state depends only on its current state. The sequence of events that preceded it is totally irrelevant.
Let me make sure I'm following this. You're saying the drone has zero memory of its flight path from, like, 10 seconds ago.
It doesn't need it. Look at it this way. If you throw a baseball and I take a snapshot of that ball midair and I know its exact current velocity, its spin, its altitude, and the current wind resistance.
You can calculate exactly where it's going to land.
Exactly. I don't need to know who threw it or how long it's been in the air. By applying the Markov property, the drone only looks at its exact altitude, pitch, and velocity right now to figure out the best move for the next fraction of a second.
Wow, that must save an unbelievable amount of computing power.
It absolutely does.
So how effective is this toddler on a boat method in practice? What kind of success rates are we actually seeing when we just let the AI figure it out via trial and error?
Well, the researchers highlight a structured approach called curriculum learning. It's exactly what it sounds like. You don't start the AI in a hurricane.
Right, you start small.
Yeah, you start the drone in a digital simulation of an empty room. Go fly forward. Then you add one stationary pillar. Go fly around it.
And then you just keep making it harder.
Right, you add moving obstacles and wind. And using this progressive curriculum, single drones actually achieved a 92% success rate in highly complex tasks.
92% is fantastic. But I remember the paper mentions a pretty significant catch here. They reached the target, but they don't always fly like a professional pilot, right?
Yeah, that's true. The AI might take a ridiculously long looping route around a simple obstacle just to be safe, instead of making a sharp, efficient turn.
And that inefficiency is sort of the crack in the foundation, isn't it? Because one drone taking a slightly wider turn in an empty sky isn't a huge deal. The environment is static.
Right.
But the real problem, the multi-agent problem, that completely explodes the moment you put 10 or 50 of these learning drones in the exact same airspace.
Exactly, because now the environment isn't static anymore. Every single drone is a moving obstacle for every other drone.
Right, and it introduces a phenomenon called non-stationarity.
Yes. Imagine trying to learn a highly choreographed ballroom dance with a partner, but your partner is actively trying to learn a completely different hip-hop routine at the exact same time.
Oh man, that sounds like a disaster.
It is. Every time you figure out where to step, they change their movement pattern and you step on their toes. From the perspective of drone A, the rules of the sky are constantly changing because drones B, C, and D are updating their flight behaviors at the exact same time.
So it's just pure mathematical chaos.
Pure chaos.
Okay, so how do we solve the non-stationarity problem? If they're all constantly changing their minds, how do we get them to, dance together?
Well, the researchers point to specific multi-agent algorithms, which fall into two main categories: value-based methods and policy-based methods.
Okay, let's break those down.
Let's look at the value-based ones first. These use algorithms with names like QMIX and MADQN. They work by continuously updating a mathematical function to estimate the value of specific state-action pairs. But these algorithms aren't designed for cinematic aerial photography, They are designed for tactical problem solving. QMIX, for instance, is incredibly effective in partially observable environments, like a military search operation where enemy locations are hidden.
Right.
It uses a structure called centralized training with decentralized execution.
Meaning they learn the strategy together on a massive supercomputer, but when they deploy into the real world, they can execute the mission independently.
Yes, exactly. You train the hive mind in a data center where the algorithm has perfect godlike knowledge of the entire grid. Then you unplug the drones, put those trained chips into the hardware, and send them into a cave with zero Wi-Fi.
Oh, wow.
They can operate flawlessly using only what their onboard sensors can see because they already learned the grid strategy. The problem with QMIX, though, is that the network structure is fixed.
So you can't add to it.
Right. If you try to add 5 more drones to the swarm mid-flight, the whole system just breaks down.
Which is where the other algorithm, MEDQN, comes in.
Right. The multi-agent deep Q network. It periodically updates its target values rather than requiring constant, heavy computation for every single move. That makes it much more scalable. You can keep adding new drones to the fleet, and the algorithm can handle the extra grid calculations without crashing.
But we're still stuck on a grid. And if we're flying through a burning forest, dodging falling branches and sudden gusts of wind, choppy grid movements are going to get the drone crushed.
Yeah, definitely.
We need smooth, continuous adjustments to throttle and pitch. So how do we get them to fly fluidly?
For that, we have to abandon the grid entirely and move to the second category policy-based methods.
Okay.
These algorithms don't bother estimating the value of moving to a specific square. Instead, they directly optimize the continuous policy function that guides the drone's actual motors. It handles the continuous spectrum of speed, pitch, thrust, and yaw.
And the paper mentions they do this using an actor-critic framework, which, I have to say, paints a completely hilarious picture in my head.
Ah, how so?
Well, you have the actor, which is the drone physically adjusting its rotors and tilting in the wind. And then you have the critic, which is like a Hollywood director sitting in a chair, analyzing the drone's performance and yelling, "No, your pitch is all wrong. Do it again, but with more thrust."
Honestly, that's an incredibly accurate way to visualize it.
Really?
Yeah. The actor is the part of the neural network that outputs the actual flight commands. The critic is a separate part of the network that evaluates those commands based on the overall goal and tells the actor how to adjust.
Oh, okay.
This constant internal feedback loop allows for much more stable, fluid learning. But finding the right algorithm to run this framework is tricky. The survey highlights one called MADDPG, but notes it requires millions of steps to train. It's just too slow.
Then the paper introduces MADTRPO, which stands for Multi-Agent Trust Region Policy Optimization.
Right.
And the key word there is trust region. From what I understand, this basically puts a mathematical leash on the AI's learning rate.
Right. That's the perfect way to describe it. It uses a highly complex mathematical boundary called a KL divergence constraint.
Okay, that sounds intense.
It is, but in plain terms, it literally just limits how much the AI is allowed to change its behavior in a single update.
Got it.
Because if a drone discovers a new maneuver that seems slightly better, it might be tempted to completely overwrite its current flying policy. But if it's wrong, it drops out of the sky.
Right, which is bad.
Very bad. The KL divergence constraint forces the drone to only make tiny incremental tweaks to its policy, keeping it within a trust region of proven, safe flight mechanics.
But calculating those complex mathematical boundaries constantly while flying through a forest, that has to require a massive amount of computing power.
It does. It requires calculating second-order derivatives, which will completely melt the limited microchips on board a standard drone.
Because you can't put a supercomputer on a tiny quadcopter. It's too heavy.
Exactly. And that brings us to the absolute superstar of the survey, MAPEO, Multi-Agent Proximal Policy Optimization. So how does MAPEO enforce that safety leash without frying the drone's processor?
It uses something called a clipped surrogate loss.
Clipped surrogate loss. Yeah. Instead of calculating those massive, complex secondary derivatives to enforce the boundary, MAPTO takes a computational shortcut. It simply calculates a proposed update to the flight path, and if the AI tries to change its behavior by more than a hard-coded limit, say 20%, the algorithm simply clips it.
It just ignores the rest.
Exactly. It ignores the excess. It says, we will update your behavior by exactly 20% and not a fraction more.
So it gets the exact same safety stability as the heavy math, but uses just a fraction of the processing power.
Yes. And because it's so lightweight, it achieves incredibly fast convergence. The drones learn their fluid, continuous maneuvers quickly. Right now, MAPO is the gold standard being used in highly advanced digital simulators like PyBullet and AirSim to teach drone swarms how to aggressively dodge dynamic obstacles in dense urban environments.
Okay, so MPO gives them the brains to fly fluidly and safely. But here's where it gets really interesting, because this brings up the next logical obstacle.
Right.
If we have 50 drones buzzing around a collapsed building, constantly adjusting their flight paths, Don't they need to talk to each other to avoid colliding? Won't they just completely jam the radio frequencies trying to share all their sensor data?
That is the exact communication bottleneck we discussed at the very beginning.
Oh, right.
If 50 drones are transmitting live, high-definition video feeds, LiDAR scans, and exact GPS coordinates back and forth over a central network, the latency will just skyrocket. The network will lag, and the drones will crash.
And plus, in military or surveillance applications, broadcasting raw video feeds creates a massive security vulnerability.
Exactly. Anyone with a receiver could intercept the data.
So how do they coordinate without clogging the bandwidth or leaking sensitive data?
Through a massive breakthrough called federated MARL. It is the ultimate hack for both privacy and bandwidth.
Okay, how does that work?
Instead of sharing their raw sensory data over the network, every single drone trains its AI locally right on its own onboard edge computing chip.
Locally. All right.
Yeah. Drone A uses its own video feed, runs the MPO algorithm, updates its own local brain, and then it only shares the model parameters with the rest of the swarm.
Wait, what exactly are model parameters in this context?
The parameters are just the updated math equations, the weights and biases of the neural network. Drone A isn't sending a video of the falling debris it just dodged. It's sending a tiny string of numbers that represents the lesson it learned from dodging the debris.
Oh, wow. It's like sending an encrypted one-page summary of a textbook instead of mailing the entire physical library to 50 different people.
That is a brilliant analogy. It's truly decentralized intelligence, and the benefits to the hardware are staggering. The survey cites a study by Young et al., which demonstrated that using this edge AI federated approach reduces communication delay by 64%.
64%? That's huge.
And because transmitting data takes significantly more battery power than doing local math, it reduces energy consumption by an astonishing 78% compared to traditional mesh networks. The drones fly longer, react faster, and the network never clogs.
That's incredible. And what about the security aspect? How does sharing the math protect the data?
Researchers use a technique where they intentionally inject mathematical static into the parameters before transmitting them. It's called Gaussian noise.
Gaussian noise.
Think of it like blurring a face in a photograph. You can still tell it's a person, and you can see they are walking to the left, but you have no idea who they are. The Gaussian noise scrambles the highly specific details of what the drone saw, protecting the privacy of the raw data, but the underlying lesson of the flight path is preserved.
So even if an adversary intercepts the transmission, they just get a scrambled equation.
Exactly.
Okay, so if the math is this dialed in, an MPPO combined with federated learning solves the brains, the bandwidth, and the privacy. Where are my drone swarms? I mean, why aren't our skies filled with perfectly coordinated, completely autonomous search and rescue fleets right now?
Well, because of something researchers call the reality gap. And this paper desperately calls out several open problems that are keeping this technology grounded.
Okay, what's the biggest one?
The biggest hurdle is turbulence. As we mentioned, almost all of this AI is currently trained in pristine, digitally simulated air.
And a computer simulation obviously doesn't have sudden, unpredictable thermal updrafts.
Exactly. Or the ground effect, where the downward thrust of the rotors bounces off the pavement and destabilizes the drone when it flies too low. Real physical aerodynamics are just chaotic.
Right.
The paper highlights the failure of transfer learning. You can take a policy trained flawlessly in a perfect simulation, drop it into a physical drone, and watch the AI completely fail to converge in the real world.
Why is that?
Because of sensory noise. A speck of dust on the camera lens, a slight vibration in the chassis, or a momentary drift in the GPS signal provides the neural network with confusing data, and the mathematical policy just breaks down.
Wow, a speck of dust. And then there has to be the issue of physical hardware failure at scale, too. Like, in a computer simulation, we can run 50 drones indefinitely. But out in the physical world, what happens to the swarm's carefully balanced hive mind when, say, 5 drones suddenly lose power due to a battery defect, or a hawk attacks one of the quadcopters?
Yeah. Ensuring fault tolerance is a massive ongoing struggle. If one agent goes down, the algorithm has to be robust enough to instantly recalculate the optimal spacing and task distribution for the remaining 49 drones without triggering a cascade of collisions.
And we just aren't fully there yet.
Not fully, no.
So what does this all mean for you, the listener? Why should you care about the nuances of surrogate loss or Gaussian noise or the reality gap.
Right.
Because overcoming these final physical barriers is the key to the future we've been promised for a decade. This rigorous mathematical foundation is exactly why we are on the absolute verge of fully autonomous fleets delivering packages directly to your backyard without human intervention. It's the architecture that will allow search and rescue swarms to autonomously sweep a collapsed building in minutes, and precision agriculture swarms to manage 1,000-acre farms drop by drop. The tech is coming. The staggering complexity of teaching machines to share a hive mind is just why it's taking a few more years to get it right.
It is a remarkable progression of technology. But as we wrap up, diving into this research raises an important question, one that actually leaves us with a final, slightly provocative scenario to ponder.
Oh, I like provocative scenarios. Let's hear it.
Throughout this entire exploration, we've talked exclusively about how a single swarm learns to cooperate with itself.
Right. We assumed all 50 drones are on the same team.
But as our skies inevitably get more crowded, what happens when two different swarms owned by two different entities meet in the same airspace?
Oh, wow.
Imagine a massive commercial delivery drone swarm running a highly aggressive, fast-moving app PPO algorithm. Suddenly, it enters the exact same physical space as a city emergency response swarm running a very conservative, heavily constrained MATRPO algorithm.
That is wild. How do two completely independent, non-communicating AI hive minds negotiate the exact same physical reality in real time without causing a massive catastrophe right above your house?
Well, they don't speak the same algorithmic language. They don't share the same goal condition rewards. So when the smoke finally clears over that burning forest and the skies open up to thousands of autonomous agents, the greatest challenge won't just be teaching a swarm how to fly. It will be teaching entirely alien AI systems how to share the sky.
And that is a fascinating thought to leave on. Thank you so much for joining us on this deep dive into the hive mind. Keep looking up, keep questioning the invisible systems that are quietly reshaping our world, and we will catch you on the next one.